We now discuss Hooke's law and elasticity. In the one-dimensional linear elastic case, our stress was proportional to strain, and we use the simple Hooke's law: stress is equal to E times strains. Our E is modulus of elasticity, which is the property of material. Therefore, in one-dimensional case, only single material property is required to relate stresses with strains. We can determine the Hooke's law in terms of three-dimensional case, but we will need more than one constant. As per our knowledge of stress and strain tensors, there are nine components of stresses and strains. In the case of three-dimensional problem, the Hooke's law states that each of the stress component is a linear function of the component of strain tensor. So we have six independent components, and each stress component is in turn a linear function of six strain components. And every strain component has got its own constant. Thus, altogether, we have 36 constants. Please note that in the case of stresses and strains, we have actually nine components. However, the components such as sigma 21, sigma 31, and sigma 32 is equal to sigma 12, sigma 13, and sigma 23. If they were not equal to sigma 12, sigma 13, sigma 23, then we would have had every stress equal to nine components of strain, and in turn we would have nine stress equations. So altogether 81 constants. 9 times 9 is equal to 81. It is because of the equilibrium of the element that we get sigma 12 equal to sigma 21. Similarly, sigma 13 equal to sigma 31, and sigma 23 equal to sigma 32, and that reduces the number of constants to 36. Now, in the case of anisotropic elasticity, which deals with the mechanical behavior of material exhibiting different properties in different directions, we would have 21 constants. Let us now discuss anisotropic elasticity and find out the number of coefficients for an anisotropic material. An anisotropic material is that material which exhibit different properties in different directions. So for example, if we have got a component, we apply load onto it and it will stretch and give us some strain. However, if that load is applied in any other direction, like in orthogonal to the first direction, we would get different stress strain. So as we change the load application point, we get different strains. That type of material is called as an isotropic material. As we have said that sigma 1 1 is equal to partial u naught by partial epsilon 1 1. We can differentiate this first equation with partial epsilon 2 2. Similarly, we can differentiate the second equation with partial epsilon 1 1. These two expressions should be the same because partial 2 u naught by partial epsilon 1 1 partial epsilon 2 2 is equal to partial 2 u naught partial epsilon 2 2 partial epsilon 1 1. And the reason they are equal is that we have got a continuum. So there is no gaps in the material. By doing so, we get C12 equal to C21. Please note that once we differentiate this first equation with respect to epsilon 2 2, everything will become 0 except epsilon 2 2. And once we differentiate the second equation with respect to epsilon 1 1, everything will become 0 except the first term. That will make C12 equal to C21. We can repeat that exercise and find that C13 is equal to C31, C23 is equal to C32, and so on so forth. Thus, in other words, all the constants which are above these diagonal are equal to the constants which are below the diagonal constants. The diagonal constants are C11, C22, C33, C44, C55, and C66. So if we count the independent coefficients, we will end up with 21. Thus, we can subtract the 6 diagonal from 36 constants, we get 30, and 15 out of 30 are dependent. So therefore we take 30 by 2 and add the 6 diagonals back, we get 21 constants. So in an anisotropic material, we would have 21 constants. In the case of isotropic material, which have the same mechanical properties in all directions, such as in case of steel, regardless of the direction of the load, our stress strain diagram will be the same. We can have C11, C22, C33, all the diagonal terms called as C1, and the non-diagonal terms called as C2. So we reduce the number of constants to only 2 in the case of isotropic elasticity. We can have other type of materials also, like orthotropic materials, but we are not discussing that in this presentation. Finally, we will try to derive an expression for strain energy. Now, from the equation shown over here, we can write that sigma 11 is equal to partial u naught by partial epsilon 11, and which is equal to this expression, which is the first equation. We can integrate this with respect to epsilon 11, and we would get the first expression would be half C11 sigma 1 square. So since the integral of this expression will give us sigma 11 square by 2, the other epsilons are constant with respect to integral of with respect to integral over epsilon 1 1. So therefore epsilon 1 1 appear in the other expressions. Since this is the integration of a partial derivative, therefore we have to add the other remaining constant. As we discussed, our strain energy density is a function of all the epsilons and the positions x1, 2, 3, and the temperature and time. We assume homogeneous material, so x1, x2, x3 dependency will go away. We assume no temperature dependence, no time dependence, so we are left with only the components of epsilons. Since we are integrating that expression with respect to epsilon 1 1, so the remaining variables will come as a constant when we integrate the expression. Therefore, the remaining variables are entered as functions. Now we will have to determine the value of each and every function. We can differentiate this expression with respect to epsilon 2 2, and we will get C12 epsilon 1 1 partial epsilon 2 by partial epsilon 2. The first expression will be 0 because epsilon 1 1 is considered not to be dependent on epsilon 2. The other expressions will also be 0 except the function of epsilon 2, which is written over here. So by partially differentiating u naught with respect to epsilon 2, we would get only two terms. Partial u naught by partial epsilon 2 is also equal to sigma 2 2 as per our previous discussion, and that is equal to this second expression. So this second expression can be written over here. Now these two expressions which are highlighted in green, they can be, their coefficients can be compared, which will give us the value of the function partial f1 by partial epsilon 2 equal to c22 epsilon 22 plus c23 epsilon 33 plus c24 epsilon 12 plus c25 gamma 13 plus c26 gamma 23. Now we can integrate this expression with respect to epsilon 2, and we would get an expression equal to C22 epsilon 22 square by 2 plus C23 epsilon 2 epsilon 3, C24 gamma 12 epsilon 2 plus C25 gamma 13 epsilon 2 plus C26 gamma 23 epsilon 2. Please note that in this expression we haven't added any constant because we are assuming homogeneous material. From here, we will get the function f1 sigma f1 epsilon 2, and we can plug that back into our expression of u naught. We will do the same exercise of finding f2 sigma 3 by first of all taking partial derivative with respect to epsilon 3, then by comparing the strain energy equation with the Hooke's law, getting the coefficients, and then integrating with respect to epsilon 3, and then plugging back the value. This exercise would be repeated for each and every constant. And finally, we will obtain a strain energy equation which will look like this. It states that strain energy is equal to half C11 epsilon 11 square plus half C12 epsilon 11 epsilon 22 plus so on so forth till half C16 epsilon 11 gamma 23. Then plus half C12 epsilon 11 epsilon 22 plus half C22 epsilon 22 square plus and so on so forth till 26. And similarly half C13, and finally we would have half C16 epsilon 11 gamma 23 plus half C26 epsilon 32 gamma 23 plus and so on so forth till half C66 gamma 23 square. This is our final strain energy density equation.